We should start. Today we are very happy to have Gregory Korchemsky from IPHT Saclay, and he's going to tell us about solving AdS CFT with strong Szego limit theorem. Over to you.
Thank you very much. So it's a great pleasure to give this talk. Thank you very much for the invitation. Unfortunately, everything goes virtually, so this seminar also is virtual. So what I'm going to tell you is based on some joint work with Andrei Belitsky, and it's based on these 3 papers which appeared over the last year. And as you could see from the title of my talk, I'm going to tell you about some recent progress in, let's say, partially solving some problems in the CFT. And also you see from the title of my talk, what it has to do, it has to do with so-called strong secure limit theory. I don't expect you to know what it is, so I will at some moment give you rather general review about this limit series. But the punchline of my talk will be just to show you that something interesting happens in AdS CFT if you start applying this very powerful mathematical machinery. And outline will be as follows. So first of all, I will be talking about computing special class of the observable in very special theory, which is planar four-dimensional maximum subsymmetric Yarmil theory. And everyone likes this theory by different reasons. And my take on this is that this is a four-dimensional theory which has a lot of things in common with, let's say, beloved four-dimensional field theory like QCD. But contrary to QCD, it has a lot of symmetries which preserve the quantum level. So, you know, conformal symmetry, no anomalies. And it also enjoys certain properties which are quite remarkable. And one of them is integrability. And integrability holds both at weak and strong coupling. And at strong coupling, AdS CFT meets nicely integrability. And people realize that indeed integrability is something which is believed to happen for arbitrary value of the coupling constant. And over the last couple of years, a lot of progress has been achieved. And just to give you a short summary, at the beginning, people solve so-called Spreckle problem. Namely, right now, we have very well-defined machinery which allows one to compute spectrum of scaling dimensions of Wilson operator in the theory in the planar limit, basically for any valued Hooft coupling constant. And it's thanks to integrability. And more recently, there was also progress in computing more complicated objects which are on shell scattering amplitudes and closely related objects which are light-like Wilson loops. So there is some duality relating one to another. And also in this case, also integrability offers you a very powerful tool for computing both quantities, basically for any value of the coupling constant. And if you continue going in this direction, trying to increase the complexity of the observable, the next logical step would be to consider correlation functions, which are definitely much more complicated than both light-like Wilson loop and amplitude, because they carry much more information. And basically the question which I would like to address during my talk, whether it's possible to compute 4-point correlation function exactly in this theory for any valued Hooft coupling constant. And for this to happen, some miracles should also happen. And actually, one of the miracles I will try to show you later on during my talk. And to be more specific, I will be considering a very special class of correlation functions. There will be correlation functions which include special operators, which are so-called half-BPS operators, which are special operators. Moreover, I will be talking about special class of half-BPS operators, which are infinitely happy. I will define in a moment what I mean by this. And so what I will show you during my talk that integrability allows you to formulate equations, which are exact equations, meaning that we will come to some point to a system of the equation which control dependence of this correlation function, both kinematic and variance of coupling constants. And those equations are exact. But as usual, when you have exact equations, it's very difficult to solve them. And I will show you 2 different limits in which those equations could be solved. And one of the limits will be a strongly coupling expansion. And at that moment, you will see that the strong Szego theorem comes as a rescue to solving a very complicated problem of solving those equations. So we will come with some expansion, with strong coupling expansion. And finally, I will show you how you could make some kind of experimental searches. Namely, we'll compare numerical evaluation of those correlation functions for moderate value coupling constant against strong coupling expansion. And we will see the comparison between the 2. So let's start. And as I already told you, the main object of my talk will be 4-point correlation functions and correlation functions involving special operators. So n equal for c, you have three complex scalars, which are normally called x, y, and z. And what we like to do, I'd like to construct a special class of half-BPS operator involving only two of those scalars. So here you have x and z. These are two complex scalars. And here I just give you some three examples of half-BPS operators. So two of them are relatively simple. The single trace operator involving arbitrary power of complex scalars x and z bar. And first one is more complicated. It involves both scalars, equal number z, equal number x bar, and there is some permutation to make it completely symmetric in certain sense. So these operators enjoy a lot of nice properties. First of all, they respect half of supersymmetries, and as a consequence, their scaling dimension equal to the number of scalar field. So this capital letter K will play an important role in all fours. So this capital letter K defines both the scaling dimension, which is protected. It does depend on the coupling constant. At the same time, it defines R charge of those operators. And supersymmetry basically tells you that R charge will be equal to scaling dimension, and that is the reason why scaling dimension is protected. So then you start constructing correlation function of those operators, and once again, supersymmetry will tell you the two and three points. Please?
Sorry, just a question. These three operators obey the same set of supersymmetries, right?
Yes, they respect, they negate the behavior of supercharges. And if you wish, these are kind of special class of operators, but if you want to construct the more general half-BPS operator, it's constructed as follows. So you have three complex scalars, so let's call it x, y, and z. And then you could take a linear combination of those complex scalars with some arbitrary coefficients, and those coefficients define you in general three-dimensional vector complex or six-dimensional real vector. So if this vector is null, then basically linear combination of six real scalars with the coefficients which form six-dimensional vector will be half-BPS operator. And these operators 1 and 2 or 3 correspond to very special choice of those null vectors in six-dimensional space. For example, this one, it will be 1 plus I. This one also 1 plus y, but in direction orthogonal to this one. And these are more complicated one. But in general, those half-BPS operators are well classified. And I have chosen three of those operators for the reason which you become clear in a second.
Thank you.
But once again, please keep in mind that there is letter K, which is arbitrary. So K could be starting from 2 because we're dealing with SU engaged group. So you have to have at least two scalars inside the trace. But apart from this, K is arbitrary integer number. So now, as I said, 2 and 3-point correlation function are protected. The simplest will be 4-point correlation function. So you take 4 operators, you look for their correlation function. And since each of the operators is protected, you could always write the 4-point correlation function in such a form, where in the denominator, I put some factor depending on the distances between locations of operators in the power, which defined by scaling dimension. And basically, this factor carries conformal weight. In what extent in numerators is a function which depends only on two cross ratios, which are conventionally called U and V. So in this particular case, the reason why I put it simplest, actually it's simplest, it's not my terminology, it's Frank Coronado who dubbed it simplest, because this correlation function has a very simple form. So namely what I did, I put operator x1, x4, the same operator, excuse me, x1, x3, x1 is point x1, x3, I put the same operator, which involves half of x and half of z scalars. Those z scalars shown here by black, and those x's by blue, and operator 2.2 and 4, these operators are 2 and 3. So the reason why these operators have been shown in such a way, because if you start to compute correlation function using Feynman rules, you will find that the Born approximation, the only diagram we will have is the one when you have k over 2 scalars stretched between each pair of points. Right? There is no other way to organize weak contraction. And this becomes a very important property, you will see later. In some sense, this Born level approximation defines you a frame in which each pair of points, 1, 2, etc., are connected exactly by k over 2 scalar propagators. And then when you start to dress it with quantum corrections, you will start, for example, putting some gluons, and those gluons will dress your frame, but the frame is always there. So if you're now thinking about choosing other correlation function, for example, you could replace here by other half-BPS operators, you will have definitely much more complicated diagrams. For example, one on my virtual background is this diagram. It's the one which will appear if you start playing different half-BPS operators. But this one is special. Once again, let me stress that in the Born approximation, it basically defines you some frame, which consists of the bunch of scalar operators. And once again, each of this bunch, it's called bridge conventionally, contains number of scalar propagators which is defined by the k. So now our goal will be to define this function calligraphic g as a function of u and v, which are cross ratios defined here. And conventionally, it's used, people used to parameterize those cross ratios in terms of the auxiliary variable z and z bar, defined like this. So later in my talk, sometimes you will see u, sometimes you will see z and z bar, but just keep in mind that those are kinematical invariants were defined by the position of the operators. And once again, we'd like to find this calligraphic function g for arbitrary values of cross ratios and for arbitrary values of Hooft coupling constant. And I will always take in planar limit. So now this correlation function, as usual, have some nice properties, and those properties appear if we go to special OP limit. So one natural OP limit, which defined in Euclidean spacetime when you collide two operators. For example, if you consider the limit when operator point x1 approaches operator point x2, or in terms of cross ratios that correspond to u2 0, v2 then OP allows you to replace the product of two operators by the OP expansion when you sum over all possible local operators which could appear in the OP with the corresponding OP coefficient. The denominator you put here delta, standing for the scaling dimension of this operator, which in general is unprotected operator. And the leading contribution will come with the operator with this minimal scaling dimension, which in this case will be k. So once you identify those operators, you will find the leading contribution will have standard form. It will be square of the corresponding OP coefficient, u, which is small in the power, which is difference between scaling dimension of the operator which appears in OP, and the k, which is dimension of the operators entering in the OP. So these are one limit. Second limit is less unconventional. It's defined in Lorentzian signature on Minkowski spacetime. And it's the limit in which you put pair of neighboring operators on the light cone. Another way, if you go back to my picture, you have this frame, and now I want to consider the limit when each edge of this frame belongs to the light cone, which corresponds to this kinematical limit, or in terms of the cross ratios, these are when both u and v goes to 0 simultaneously. So this could be thought like if you have a null rectangle and you put operators as a vertices of the rectangle, or in terms of cross ratio, it's convenient to define variables y and xi. So one of them is log of the product, which obviously goes to infinity, and another stay fixed in this limit. So you have one variable which is large, another fixed, and then you ask the question, what will happen with the correlation function in this particular limit? So similar to the previous case, you're running OP, but different with respect to previous case, that now the dominant contribution will come from the operator with arbitrary large Lorentz spin S. So because of this factor here, u and some power, you see that this combination, which actually twist of the operators which are changed, once you go to the limit when u goes to 0, the dominant contribution will come from the operator with a minimal twist, but with arbitrary large spin S. And it comes with OP coefficient squared, collinear from a block. And then you could argue that if you go to the limit when u goes to 0, v goes to 0, contribution of large spin could be resummed, and schematically it takes a form of exponential factor, exponentially small factor. With the exponent, you have in general whole series, but the leading term will be quadratic in y, or if you wish, it will be double logarithmic in the cross ratios with some coefficients which are functions of the coupling constant. And in general, this function of the coupling constant should depend on the k, of the scaling dimension of the operators which you have at the beginning. So later you will see this formula appearing, and later I will give you exact formula for the function gamma. So very good. So these are general properties. Now let's try to compute this correlation function. And as usual, we start with, please go on.
One question. In the previous slide, you had this u and v both going to 0 limit.
Yes.
There is a way to take this limit without sending all of them to the vertices of the null rectangle, right?
Yes.
So 3 of them could be Euclidean separated, and then one of them could be in the light-like separated from the 2 others. That also would give you this limit, right?
No. Look at this. So if you're in Euclidean spacetime, so let's think about cross ratios. So as soon as you take x1, x2 be null separated, let's say x1 minus x2 squared. So if in Euclidean spacetime, it means that this point coincide. If they coincide, you automatically go to the limit u to 0, v to 1. So if you want to be U in one independent, let's say if you want to have limit such a way that use arbitrary whereas V to one, you have to go to Minkowski spacetime. Without going to Minkowski spacetime,
I meant that 3 of them are space-like separated, and then one of them could be light-like separated from the 2 others. That also should do it, right? That is the more standard in the Z bar plane. You just go to the tip of the square.
So let's do what you just said. So you take, let's say x1, x2 be null separated. So U goes to 0, obviously, but V. So if you just keep a Minkowski signature, V is arbitrary, right?
Well, I want to set x12 to 0 and x23 to 0.
I see.
Not anything else.
Yeah, I see your point. Well, I don't see right now. I don't see any abstraction. Maybe you're right, but I have to think just to give you. Let me think a little bit. Probably you're right, but I cannot tell right away whether.
Okay, fine.
Mm-hmm. Okay, I'll think about it. So now let's now do V-coupling calculation. So V-coupling calculation, basically you open Feynman diagram and just write correlation function expansion of powers coupling constant. So one.
Hello.
Please.
Hello. Sorry, if I may interrupt. Maybe this is obvious from what you have said, but so to understand that like in this this GK UV, the function of U comma V, it has in principle infinite number of functions of the Hooft coupling. Its information is not characterized by any finite number of functions of lambda. Is that?
Sorry, I didn't hear you well. Could you repeat, please, your question? Is there some echo going on?
Sorry. Is there some? I mean, using all the supersymmetry and so on, like, can we reduce the number of information in GK U comma V into some finite number of functions of the Hooft coupling, or are there infinite number of functions involved?
Okay, wait a second. So the first answer to your question will be infinite number of functions, but probably the question you'd like to ask differently is that you may associate certain complexity to those functions, right? So imagine thinking about logarithms, right? Logarithms, it's a nice function. Log square, it's also a nice function, but its complexity is the same as logarithms. But if you go, for example, to more complicated function like dialog, definitely the function have much more complexity because they have more complicated analytical structure. So if I were to formulate the equation, do you expect to have some simple class of function appearing, or are you expecting to this function have increasing complexity if you start going to higher number of loops? Is it question?
Yeah, and also whether whether you can reduce it to some one function or something. Because honestly, it looks like a very hard problem to kind of determine a full infinite number of functions of lambda.
So the short answer to your question would be that at strong coupling, we will see that indeed you will be basically, if you go to strong coupling, if you ask in the question what kind of function you expecting to find, indeed you will find there will be the same function appearing. I will show you later. At V-coupling situation a bit more complicated, and actually I will just go through V-coupling and you will see answer to this question appearing.
Okay, thanks.
Just be with me at V-coupling, you will see now, next slide, you will see these functions appearing. But for the moment, I just want to give you just general overview of what you're expecting if you use conventional approach. You just run a Feynman diagram. For example, here I have shown you few Feynman diagrams which contributing to this correlation function. And I have chosen, for simplicity, that k equal to 2. So in each of the vertices of my correlation function, I have only 2 scalars. That is the reason why you have this very simple diagram appearing. And then you have gluon exchange, you have cortex scalar exchange here, and here you have Yukawa coupling with the Fermion loop, etc., etc. The many diagrams. And then, as usual, with Feynman diagram, for example, these 2 diagrams, they will depend on the gauge which you're using to compute gluon contribution. And therefore, there is no chance that there will be neither gauge invariant nor conformal invariant. And for example, these two diagrams will have in addition UV divergences, but you're more or less expecting in series finite UV divergence should go away. Anyway, you see that there is a lot of mass already at one loop. But if you sum all the diagrams together, taking care of regularization, etc., you will find that the sum of all those diagrams becomes remarkably simple. Namely, at the end of the day, you could show that at one loop level, all diagrams sum up into a very simple integral, which is shown right here. And just to give you an idea about this integral, it's convenient to depict it as follows. So you have 1, 2, 3, and 4. These are points when you insert external operators, and 0 integration point. And this integration point is connected with external points by 4 scalar propagators. So once again, this is not the Feynman diagram which you will see here. This appears as a result of the summing of all diagrams. And this integral is easy to convince yourself that it's conformally invariant, basically because you have four-dimensional integration measure, and you have 4 scalar propagator attached. At the moment, number of scalar propagator matches integration space, dimension space-time respect to which you're integrating. It's already convenient, sufficient to show that it's conformally invariant. So this becomes the function which appears at one loop, and the explicit expression you will see at the next slide. And now you could imagine if you go to 2 loop, and etc., then complexity will increase enormously, and there is no way you could go and compute explicitly those integrals beyond 2 loop. But there is much more efficient approach, and the approach is the following: that if you knew what kind of function or what kind of integral will appear as expression of this correlation function, you could then apply this OPU limit, which I described before, just to fix the coefficient in front of the conformal integrals which appear a given number of loops. So these are much more efficient approach because it avoids you to go through Feynman diagrams. It's just sufficient that you knew the basis, you apply OP expansion looking for different limits, and you fix the coefficients. It's much easier. And this also will give you a clue what kind of function, what kind of integral will appear at V coupling. And here's the answer. So this analysis has been performed, and it's
Grisha, just a basic question.
yes.
The one you had at 0 loop, I mean 1, the leading contribution was 1. Was it the contribution of the square diagram?
No. Once again, first of all, let's think about this diagram. So this diagram, you see, you have this frame, and you remember this definition of calligraphic G. It was here. So I put in denominator. So let's put k equal to 2 here, right? K equal to 2 will tell you that correlation function, it has this frame for scalar propagator in denominator, and some calligraphic function G in numerator. So each of this diagram, with this diagram, you see it has this frame. So basically, you write this representation, write this integral of positions to gluons, and then you have to divide this by the 4 scalar propagator, and you will get something.
Yeah, I got it. Yeah, I didn't realize that the factor that was pulled out was different than the conventional one. Okay.
And now you see that if you now take this integral is G, right? So if you want to come back and you ask yourself how it will look, how its contribution to the correlation function will look like, you have to divide it by 4 propagators which are connecting external points. And then you will have a diagram which is not here, right? Such diagram does not exist in the first line. That is what I'm saying, that these are not part of the Feynman diagram basis which you will find explicitly. It comes out as a result of the consolidation between different contributions.
Okay.
Which is not surprising, once again, because in some sense, this is the only conformally invariant integral you could write at one loop. And since you knew that the result conformally invariant, it was more or less expected it should be there. It's less trivial if you go to higher number of loops. And what happens that if...
did you do your one loop calculation in position space? Is that the easiest way to do it?
Yes. Actually, well, the truth is, some people originally this result, it wasn't my result. The result was obtained by people like 2 decades ago, and they did it calculation in superspace. You could do some simplification by using supergraph calculations, but by now there is much more efficient way how to could compute some of those diagrams explicitly. But if you want to do calculation, it's much easier to compute configuration space indeed.
Thank you.
So now talking about basis conformal integrals. So this basis could be constructed using yet another properties of an equal for theory, which if you wish I could tell you later on, but let me just summarize the result. So some result is the following, that if you're thinking about all possible integrals, or if you wish, all possible functions which will appear at V coupling, order by order in V coupling expansion, you will find that those functions or integrals could be separated in 2 different classes. One is so-called simplest ladder integrals, and integral, called ladder integrals, is depicted here. So in the previous slide, you just had only one integration point, but now you have arbitrary. So you see all these points. There's a point with respect to which you're integrating, and you could see that there is exactly 4-scalar propagator attached to each point. So therefore, this integral is conformal. And actually, this integral has also a long story. It had been computed already 3-4 decades ago, and they're given by this formula. When you have sum over polylogs with variables z and z bar, which are related across ratios. So this is an explicit formula which involve product of log and dilogs. And there is yet another more complicated integrals, which appear starting from 3 loops. And those integrals, I didn't dare to write them because, as I wrote here, they involve a few pages of so-called Goncharov polylogarithms, which are functioning way more complicated than just classical polylogs. So answering to the question which had been asked before, you see that at V-coupling expansion, basically you're dealing with a simple class of functions, which are ladder integrals, and at some sufficiently high number of loops, you expect to have some monsters which are way more complicated.
So can we give an example of this Goncharov polylog in terms of the picture?
I have to refer you to one of my papers.
Okay.
First of all, Goncharov polylogs. Let me first give you a definition of Goncharov polylogs. So if you think about dialogue, so dialogue, you could think about thinking like integration of function with the measure dx over x. So you're writing integral dx over x, which obviously logarithms, but now you're writing nested integral dx1 over x1, dx2 over x2, which is obviously, and integration with respect to x1 goes to upper limit which depend on x1. So it's log square, right? But now writing in denominator x1 minus a1, x2 minus a2. So this will be integral, which could be computed, and it will be given by a bunch of the dialogues. But now start to iterating this. So you have triple integrals, 4 quartic integrals, etc., etc. Those will be integrals which in general are not expressible in terms of the classical dialogues, polylogs, and those are called Goncharov polylogs.
Okay.
So those functions have a lot of interesting properties, but one of the properties which is kind of very mysterious, or if you wish, complicates things enormously, there is no complete base of the function. Another way, on the level of the dialogues, you know that up to certain class of functions, you know full basis. Another way, if you come with a function which is dialogue of certain arguments, there is certain relation which allows you to write terms of function which have simple argument. Such kind of identities for Goncharov polylogs are not known in general, and therefore you have to deal with quite complicated base of function without knowing whether the basis is complete or not. Just to give you ideas, these are complicated functions, but if you wish, I could give you later references to the literature where you could find those functions. Actually, historically, those functions first appeared in the study of scattering amplitudes, and later people realized that the same functions also make their appearance inside the correlation function. So once again, these are kind of general basis of conformal integrals, which you expect to appear in 4-point correlation function of half-BPS operators for arbitrary choice of half-BPS operators. But we're dealing with special class of the operator. I remind you, right? We have chosen special operators to have this frame, etc., etc. And then something interesting happens. Namely, if you start looking carefully how the expansion looks like, you will find that those complicated integrals which I mentioned appear a number of loops which are correlated with this R-charge of the operators. Another way, if you take k equal to 2, as in my previous case, you will see that this integral will appear only at 3 loop. So up to 2 loop, including 2 loop, you have only simple ladder integrals. But starting from 3 loop, you have this Goncharov polylogs making their appearance. So now if you go to operators with large k, you will push complicated function to higher number of loops, which automatically tells you that something should happen if k goes to infinity, and this is the limit which I will discuss in a moment. Secondly, if you just keep only those ladder integrals, so if you just look for the expression for this calligraphic g up to number of loops, which is k, so you throw away all Goncharov polylogs, you just look for what left over. So what left over will be some multilinear combination of the ladder integrals, those integrals here, and then you will find that they have a tendency to square, to form complete square. So in this sense, it's convenient to write this calligraphic g in the form of square of some function O, and this O is given by formula like this when you have, once again, sum of a number of loops, and for any given number of loops, you're dealing with a multilinear combination of this relatively simple ladder integral with some rational coefficient d. Right? And once again, these two formulas together are valid up to corrections which appear at order k plus 1. And now the key point. Let's go now to the limit when for fixed coupling constant g, you're sending k to infinity. So what will happen? This formula will tell you that this term basically will go to infinite number of loops, which means that any given number of loops at any order of the coupling expansion, this term is absent, and you're expecting to find this calligraphic g to be given by the square of something which is multilinear combination of ladder integrals. And this is a normal simplification. This is what I mentioned before, that in this particular limit, you forget about complicated functions, Goncharov functions. You're dealing only with a class of multilinear combination of ladder integrals. So this relation, once again, has been observed empirically at V coupling, and the main question is what's the origin, right? So it's definitely tell you something. And at this moment, integrability.
Sorry, could I ask?
Yes, sure.
The number of you said the number of integrals that appears at any given loop order, did I understand right, was finite?
Yes, yes.
Including with these complicated Goncharov polynomials?
Yes. At V coupling. At V coupling. We're talking about V coupling. A fixed number of loops, but it's kind of normal, right? If you fix number of loops, the number of Feynman diagrams is finite. It may increase factorially with loop order, but the number is finite, right?
Right. And how does this number scale with k?
It scales as a power. Number of conformal integral scales as a power, but exact exponent I can tell you right away by two reasons. First reason that explicit construction of this basis has been done so far up to 10 loops. So if you look for these numbers, so this number of integrals which you ask me, those numbers are known explicitly up to 10 loops. Okay. And if you look at those numbers, how the scales with number of loops, you will see power-like behavior, not factorial behavior, power-like behavior.
And this power-like behavior, even for the simple guys, right? These ladder guys.
Yes, actually, for ladders, you could do calculation yourself. Basically, you're asking. There's a formula could give you a clue. So the general form of is like this. So you see that each of these ladder integral. Let's go back to my ladder integral. So you see that this ladder integral is given by a combination which involves power of the logs and power of dilogs. And then it makes sense to give certain definition of weight of the function. So let's give to the logarithms weight 1. So logarithms power m has weight m. And dialog has a weight which is index to L minus m. And then you will see that each term in the sum has weight 2L, right? So it's weight 2L. So that's why function fL has weight 2L. And now, if you look for the sum, this sum tells you that the final expression will involve multilinear combination of ladder integrals such that the total weight of this multilinear combination will be equal to the twice number of loops. So therefore, now you ask question, combinatorial questions. How many multilinear combinations construct such that each of these functions carries index I from 1 to n, and so that their sum equal to L. So if I'm not mistaken, it will be 2 power L. So once again, the number of terms in the sum is finite. It increases as a power number of loops, but it's finite. I'm not sure. Is it clear what I said?
Yes, very clear. Thank you.
So now let's please.
Sorry, one more question. So is there a way to define this transcendentality or whatever rigorously? And why is it that loop order at a given loop order, given transcendentality only appears?
This is a very good question. And as a matter of fact, nobody knows the answer to this question. But what we do know that so this property which I just mentioned is called uniform transcendentality property of unequal force theory. It has been observed in many different instances, starting from the anomalous dimension, passing to scattering amplitudes, and now I'm talking about the same properties level of the correlation function. We don't know the origin of this property, because once again, this origin of this property has to do with this class of function which appear in the expression for different quantities. But we do know that it's there. Moreover, now there exists a whole machinery how just only using this particular property, namely that you're expecting that contribution should have certain weight, you could bootstrap expressions for different coordinates in equal force theory. But once again, we don't know where this property comes from, but we know that it's ultimately tied to integrability.
I see. But what is to begin with the definition of transcendentality? Is there a
definition of transcendentality? It's this definition which was given by mathematicians, and definition of transcendentality goes. If you remember the way how I define Goncharov polylogarithms, you defining these nested integrals, which are mathematicians called chain integrals. And then those iterated integrals, they have integration measure, which is d log of something. dx of x is d log. And then if you have iterated integrals, which involves number of d logs equal to certain number, this number is called weight.
Okay.
And then you could check that, let's say, d logs or polylogs, they could be written in such a way. And that is the reason why this subscript here is indeed related to the number of d-log integration entering definition of polylogs.
So there's some statement about this being a vector space with some dimension which is spanned by this basis and so on.
What you just said, it's true only for dialog and I believe for trilog. Starting from Lie4, it's not true. Let's say if you're writing full basis of Lie4 with different arguments, you know, x, 1 minus x, 1 of x, then starting from weight 4, the relation between those, they're not linear independent, but for weight 2 and for weight 3, they're linear independent.
So it's just an observation that in this particular case, only a particular subspace contributes, and the basis of that subspace is this one that you're written down.
Yes.
Sorry, one more question. In the study of anomalous dimensions of single trace operators, something special also appeared at when the number of loops became equal to the total number of operators in the trace.
Yes.
The wrapping interactions started playing a role there.
Yes.
You seem to be seeing a similar phenomenon. I was wondering whether there was a connection between these two things.
It's not. There is a connection. There is a connection. And actually, connection goes like this. So, as you correctly pointed out, so if, for example, if you take a single trace operator, bunch of scalars, so putting a lot of scalars one after another. So it's not half-BPS, so it's unprotected operators. Then, indeed, there is a question at which level you start talking about these wrapping corrections. And the wrapping corrections appear normally as a number of loops which are related to the length of the operator, which k in my case. So now, what I'm playing here, I'm playing a game when I'm saying k to infinity, or in case of the single trace operators, is a situation when I'm talking about the limit when my operator becomes infinitely long. So I'm pushing these wrapping corrections to infinite number of loops. Another way, in this limit, you don't have wrapping corrections. So now, you may ask the question, at which moment this absence of wrapping correction becomes important for correlation function. And this is what I'm going to tell you in a second.
Thank you.
So as I already mentioned, now our goal, we'd like to find some arguments, some logical explanation for this property, why in the limit when k goes to infinity, and I remind you, k is the number of scalars on each of the vertex, why in this particular limit, some simplification happens, and what's the meaning of this calligraphic O? And this comes from integrability. So there was some recent progress in integrability program for computing C in 4-point correlation function. And finally, it could be summarized as follows. So let's think about the correlation function. So these are our 4-point correlation function. I'm thinking about kind of net of Feynman diagrams as a planar limit. So the planar limit, you're expecting those diagrams to form some kind of two-dimensional surface in the color space. And now you have this two-dimensional surface shown here in gray with the 4 holes corresponding to insertion of 4 operators. So you have 1, 2, 3, 4 operators. And as I already mentioned, each pair of the operators connected by the bridge. Remember, those colors propagators stretch between pairs of points. So each of these pair of operators connected by exactly k over two scalar propagators, which are over here. And now what integrability tells you, you could think about the same surface as some kind of the two-dimensional target space on which you have excitation propagating from one operator to another. So another way you switch completely logic is thinking about the same diagram as being some kind of diagram in two-dimensional space-time where excitation propagating on this two-dimensional surface between different operators and across different edges of my diagram. So then what will happen if excitation propagating, for example, across this bridge? So once again, here you have a bunch of scalar propagators. Scalar propagator is k. And now if you're thinking already at V coupling, so imagine you have a gluon which have to go through k over two scalar propagator. Obviously, if you have to propagate through k over two scalar propagators, the planar limit, it should possible only if it interacts with each of the scalars subsequently. Another way, this transition will come with a factor of g square, and the power of g square will be related to the k. And if k goes to infinity, obviously it will be suppressed. So already at V coupling, you would see that excitation propagating across each of these bridges will be suppressed. So only possibility of excitation propagate will be just on this single sheet, which we have here. And this already tells you that in this limit case to infinity, if you buy this picture of two-dimensional integrable excitations, you already could write factorized formula, which basically consequences of the fact that excitation couldn't propagate across those bridges. So this is how it comes up with this picture. So this picture tells you that this diagram, this two-dimensional picture, should be factored out in the product of something which contains diagram shown here. So this diagram shown here is octagon. Why it's octagon? Because you have 4 bridges, which are called virtual edges, those shown here by dashes. And here you have 4 portions which come from 4 operators. So this portion shown here by solid, this is some part of the physical operators. In total, you have 4 physical operators, 4 virtual edges. In total is 8. So these are called octagon. So this automatically tells you that this integrability picture immediately leads to the representation that our correlation function should be square of something. And the something describe propagation of these two-dimensional excitations on this octagon surface. So the next step also comes from integrability. Integrability allows you to bootstrap. If you put certain axioms, if you know spectral properties of these excitations, in other words, dependence of the energy of two-dimensional momenta, you could write a lot of axioms which more or less will fix your object completely. And this has been done. Please?
Sorry, the 2 octagons, do they have, do each have half of the external operators?
Yes, yes. You basically what you do, you cut, think about the surface. You cut it like this, and you cut it like that. So this way you open it up, and then you could construct the original surface by gluing together 2 copies of the octagon along those virtual edges, right? So if you're thinking about these 2 copies of the octagon and you're gluing along these dashed edges, then you will collect them together, combine together, you will get the original surface. So then each of these octagon could be decomposed further. Namely, you're thinking about just drawing some imaginary line here. And then you're saying here a full set of the states which are propagating along this cut. And this way you could now chop this octagon into 2 hexagons, summed of all excitation moving from one hexagon to another. So this is how you come to this formula. So once again, you start with octagon and you write it as a sum of all set of the states, those excitation which I mentioned before. More or less, you know everything about them. And each of these hexagon comes with a form factor, something which you call form factor, which depends obviously on the properties of the excitation which you exchanged, and the number of this excitation could be arbitrary. So in some sense, you start from the object which was defined like octagon, and you write it as an infinite sum of 2 auxiliary hexagon form factors summed over infinite number of intermediate states. And once again, integrability gives you well-defined representation for each of these form factors. It's some very compact formula which I didn't want to write you, but just simply want to mention you that the infinite sum. You have to change no particles, 1 particle, 3 particles, any number of particles. So then, in principle, this is a complicated sum you have to carry out. Some simplification happens at V coupling. At V coupling, could show that each of these hexagon form factors scales as a coupling constant in the power of the number of excitations. And therefore, if you're staying at the level of 1 loop, you have 1 excitations. If you increase 2 excitations, you have finite number of loops, etc., etc. So this is how the sum could be converted in finite number of terms. And at weak coupling, it has been shown by Coronado that if you just expand the power of the coupling constant, you reproduce exactly the same representation you have seen before. So this representation which you have here, which was a result of the explicit Feynman diagram calculation, has been reproduced using this bootstrap integrability bootstrap approach with the coefficients and the functions exactly those which appear in the explicit Feynman diagram calculation. So this was a very strong argument why this whole picture is self-consistent and why it should work for any value of the coupling constant.
The correlation function itself is gauge invariant. But when you cut it into this octagon, there are some gauge indices hanging at the edges?
No. By the construction, you start from this picture. So those excitations which I mentioned here, by definition, is a gauge invariant objects. Coming back to what I discussed before, think about single trace operator. So imagine you have single trace operator with a lot of scalars. So you start from BMN, so-called BMN vacuum. So you start from the operator like trace x power k, one of my operators. So you have so-called BMN vacuum. So these are states which are preserved by supersymmetry. And now you're replacing some of the x's by some other scalars. So you excite your vacuum state. So then integrability from point of Feynman diagram, it corresponds by replacing one scalar by another scalar. So you're just drawing Feynman diagrams, you're computing what you obtain. From point of integrability, you interpret the insertion of new scalars like exciting your vacuum. So you associate this particular diagram with excitation. So this particle psi which appears here, it becomes excitation on top of this vacuum. And these excitations described by some quantities which you deduce from explicit calculation of correlation function. In other words, the special relation for those quantities are extracted from the computing of gauge invariant correlation functions. So in this way, from the very beginning of this integrability approach, you're dealing only with gauge invariant quantities. There is no gauge dependence whatsoever.
I'm probably asking something stupid, but suppose I had trace x squared and I cut it into x and x. There are some gauge indices hanging out, right? What happens to those?
Let's do what you just said. So you put here everywhere something which is bilinear in scalar. So as I mentioned, first thing which will happen is that each of these bridges becomes one scalar. So therefore, this picture here, basically what shown here by the black line, it stands for nothing. So there is nothing you could attach to it. So you have to think about the diagram not in terms of Feynman diagram, but in terms of two-dimensional surface. So you're saying that here you have nothing on these solid edges. Nothing could be emitted out of these lines. But however, you could have, for example, gluon, which are going through each of these edges. For example, since here, let's go back. Let's go back to my diagram. Let's take this diagram. So let's take this diagram. So in this hexagon approach, octagon approach, you basically resolve these local vertices by some circle. And then, so what you have here, these four edges, it becomes these mirror edges, those dashed line. And now what the diagram tells you? The diagram tells you that you have gluons which propagates across both edges, right?
Yes.
So if you go to my diagram, it will correspond in this situation that you have those wingling line not going on these octagon patches. It will go from one octagon to another one. So thinking about second octagon here, and then you will have gluon emitted from this octagon absorbed by another octagon. So it will be gluon going across the edge. Okay. It's not Feynman diagram per se. It's something which you construct using this integrability approach. And then the question is, if you just following the integrability rule and computing this particular transition, will it match or not the Feynman diagram which you've seen at the very beginning? And the answer is it will match some of all diagrams. So this gauge invariant quantity here, this integral appears as a result of taking into account contribution of gluons which are going across these edges.
I see. So the psi here, roughly speaking, should I think of it as the Hilbert space of the string world sheet, the closed string world sheet?
Which side? Psi. It's if you go strong coupling. So let's do this way. So if you go to strong coupling, you could think about this world sheet as being world sheet of string on the just 5 crosses 5. So okay. Then you're asking what are excitation of this world sheet of the world sheet of the string.
Okay. Thank you. I think I understand.
So this will be an analog of this psi strong coupling. But the power integrability approach, it allows you to define those excitation for arbitrary value of the coupling constant. So as soon as you go away from strong coupling, you don't have Lagrangian description of the theory. But you have integrability, which tells you that bootstrapping, it allows you to bootstrap your object without specifying which series, what Lagrange formulation your series is.
So can you cut this octagon through the middle vertically?
You mean you want to cut it like that?
Yeah.
Not, because here, what's special about these solid edges and dashed edges? So once again, these solid edges, they came from external operators. External operators, BMN operators. These are protected operators. Protected operators synonymous. They cannot excite. They cannot emit excitations. So once again, this picture, these excitations, they could be emitted, say going through the edge, but they cannot be attached to the solid lines. So when you're cutting like this, when you're cutting like this, you're cutting through the edges from which there is no excitations will be emitted. So if you were cutting through the dashed line, it will be like you have like spin chain, you're dividing spin chain of the two. So you have a right and left hand side which could talk to each other.
Right. I mean, if you were to do that, then this this decomposition would be kind of like a conformal block decomposition, right? Because those would be 3-point functions and so on. That's why
actually historically this paper, this original paper, Bessel, Komatsu, Viera, they propose this approach for describing 3-point correlation function. So if you start with 3-point correlation function, you always cut it into 2 hexagons. And actually, a hexagon first appeared in the description of 3-point correlation function. Later, this approach had been generalized for 4-point correlation functions through this very smart construction by these people, by gluing together 2 different hexagon into octagon.
Okay, thank you.
And then Coronado was the first who recognized that, as I mentioned, if these operators were k equal to 2, if they had finite number of scalars, then you will have to take into account contribution of the excitation going through the edges, these virtual edges. And Coronado recognized that in this limit k to infinity, those excitations are suppressed, and therefore you get octagon as kind of fundamental object you have to deal with. And in this way, you see that this formula nicely matches what we knew from V-coupling. And now, as advantage, you have alternative formulation of the octagon, which is finite for arbitrary value of the coupling constant, but it's formulated in terms of this artificial object, which are hexagon form factors and those excitations. Okay. These completely different formulations, which appears thanks to integrability.
Nice.
And now what I want to do, I want to make use of this representation to see how far we can go in computing this object. For example, strong coupling. So now the next question, what should we expect as strong coupling? And as an example, let me take the simplest object in equal theory, which had been computed exactly, the circle of Wilson loop. So you take a circle in the Minkowski spacetime, and you're integrating gauge fields together with one component of the scalar field. So this becomes object which is kind of supersymmetric Wilson loop. And then it has been computed first in planar in equal 4, but actually now there is this explicit expression which valid for any number of colors. But for the moment, I just need only planar results. So this result has been obtained by 2 different techniques. First, it was observed that it comes from computing of contribution of so-called rainbow diagrams, which could be resummed to the matrix models. And later, Peston has recognized the same matrix models appears through localization in equal 4. Anyway, so this becomes explicit expression which valid for any value of Hooft coupling constant, some Bessel function with index 1. And then you could play with this expression, for example, going to strong coupling. If you go to strong coupling, okay, property of Bessel function will tell you that it could be written exponential, and the exponent you have series which goes in powers of 1 square root of lambda, the leading 1 square root of lambda, then there is some log terms, and then the whole series. And later people recognize that the same representation could be obtained if you're starting from a CFT description, in which case this becomes exponential function, becomes a result of computing minimal area. So you have first term comes from computing minimal area attached to the circle on the boundary DS5. Then you talking about fluctuation of the minimal surface, that it will give you terms which are enhanced by the logarithm of the coupling constant, some constant term. And then in principle, if you knew how to compute high order fluctuations, you should be able to reproduce those coefficients analytically. And let me mention that so far, nobody was able to compute those coefficients analytically, even though you know analytical expression. So far, we know only first 3 coefficients from a CFT. So now if you go to octagon, so octagon is more complicated object than circle Wilson loop, Nevertheless, it was argued by these people that it could meet the same semi-classical description. Once again, you start from the Feynman diagram when you have these 4 operators. Each pair of operators connected by this bridge scalar propagator with number of scalar propagators going to infinity, and they have argued that in the limit of strong coupling, this object admits semi-classical descriptions as if you were started from computing static amplitude of 4 closed string at ds5 cross s5, and you were approximating the static amplitude by kind of saddle point inside the partial integral, and saddle point will correspond to computing minimal area, which is attached to 4 geodesics. So each of these solid line corresponds to some geodesics on the ds5 cross s5, and each portion of the geodesics rotates on the s5 according to the R charge defined by the scalars. For example, these scalars shown in black, they were defining by operators involving these. They correspond to some equator on the sphere. Red one correspond to the axis. This is another equator, and the consequence, each of these red and black portions, they rotating on the S5 in different equators. So it becomes well-defined mathematical problem how to compute this minimal area, but as a matter of fact, nobody succeeded in computing it analytically so far. So what has been done instead, that people used this previous integrability representation in the strong coupling limit using some called clustering procedure, and they were able to find the leading contribution. So leading contribution comes here in the exponent with factor of g. So I remind you that we're dealing with in classical expansion, so therefore you're expecting to have expansion with leading term of g, log g, etc., etc., and then leading term turned out to have very compact representation. This representation moves some integral, and for those of you who know TBA and ZATs, it looks like if you are solving some TBA equation, but nobody actually knows what interpretation it takes. Anyway, so there's a very compact representation for the leading term with y and psi, those variables which are related to cross ratios, which are arbitrary here. So g is large, but y and psi arbitrary. And once again, A1, which logically should come from calculation of quadratic fluctuation, it hasn't been computed either, and it seems to be too complicated to do. So this is the status of strong coupling.
So is the AdS CFT picture true only at large K or more generally?
Yes, yeah, no. If you were to compute, let's take this correlation function, and once again, let's take, for example, k equal 2. So k equal 2 is the simplest operator trace phi square. So if you were to compute the same 4-point correlation function on ds5 cross s5, you immediately draw Witten diagrams. So it will be conventional Witten diagrams when you integrate of the point in the bulk boundary propagator, etc., etc. Here, we're talking about the limit. So in these Witten diagrams, they define the limit when you first send g to infinity, keeping scaling dimension of the operator finite. Now we're doing something opposite. First, we send scaling dimension to the operator to infinity, and then start to putting g to infinity. So this is the different limit. That is the reason why two different pictures have completely different description from point of view ds5 cross s5. In one case, you have Witten diagram, but there is no semi-classical expansion. Whereas in this case, you do have semi-classical expansion, which exponentially small factor defined by the minimal area. These are two different limits.
Since you had that the correlation function of your operators was this octagon squared,
Yes.
there should be some way of squaring that picture you showed us in AdS CFT and seeing that we get the picture we would expect to compute the correlation function.
It's actually, there is a square, because if this minimal area, it corresponds to the wall sheet of closed string. And closed string, it consists of two patches. So if you're just thinking about it's squashed wall sheet of the closed string. So there is something on the up, something on the bottom, and they're just glued together. So basically, what you're computing here, this octagon, computing area of the portion which you see from the above, but the same portion from below.
So it's a very singular kind of closed sheet.
So again?
It's a very singular kind of, the whole surface is very singular because one on top of the other.
Exactly. Okay,
exactly. Thank you.
Exactly. So, but now, once again, so we have kind of V-coupling expansion of the octagon. Now we have strong coupling expansion of the octagon, and we have this nice representation, which I have shown you here. Now the question is, could you use the representation to get something for finite coupling constant? And at that moment, some miracle happened. And to describe this miracle, let me go a bit outside the topic of my talk. Namely, if you're thinking about in general, two-dimensional integrable model. So I told you that this octagon appeared from integrability picture correlation function, and then you are go into field two-dimensional integrable models, and you ask the question, do people encounter such kind of object like octagon? And I remind you, the octagon was given by the sum of two form factors, sum of intermediate states. And if you're thinking about two-point function integrable models, you're just taking two local operators, G1 and G2, and you're computing something with respect to some vacuum. Then obviously you'll get the same sum with intermediate states, basically in any integrable model, not necessarily integrable, in any model. So what's special about integrable models, and it has been observed a long time ago by these people, that it turned out that if you plug in known expression for those form factors in many different instances, this sum turned out to be numerically related to the determinant of certain infinite dimensional operator. So this operator H, it depends on the model. But in various integrable models, it always such object needs such representation. So it looks like this representation is universal, whereas H depends on the tail of the model. So in other words, if you have integrability, you're more or less expecting that such kind of the objects, some intermediate states, should be at the end of the day be related to the so-called Fredholm determinant of certain integral operator H. And indeed, it has been observed by Ivan Kostov, Valentina Petkova, Dina Serban, that if you carry out the sum, in the case of the octagon, of those mirror particles, they were able to cast the sum into the form of the square root of the determinant of the semi-infinite dimensional matrices. So these are a representation, and let me just give you some ingredients. So there is lambda, which is scalar factor, and C and K is the same infinite matrices. So lambda is some factor which depends only on Y variables, and C, some matrix which has only two diagonal parallel to the linear diagram, but the most complicated piece is this matrix K. So all of this is NM run from 0 to infinity, so the same infinite matrix. It involves as the integral of the product of two Bessel function, and you see here G, Xi, and Y scattered across the formula. It's quite complicated formula. But anyway, these are finite coupling representation for octagon. So if you knew how to compute these objects, you're done. But as I said, the problem is that this object is too complicated. Now, if you go to V coupling, so each of these Bessel scales at small coupling like G in the power of index. And you see that if you just fix order in G, you could safely replace each of these Bessel by the series expansion. And this way you could simplify this matrix K to be a finite dimensional one. And this basically will tell you that as soon as you're dealing with finite number of loops, this octagon, this determinant, could be written as a some powers coupling constant with some coefficient, and those coefficients turned out to be exactly those which you expected to find. So there's a multilinear combinational ladder integrals. So somehow this matrix K secretly knows about ladder integrals, which is what you'd expect, right? Because he knew that this representation should be there. Very good. So now you have finite coupling representation, but the question is how to compute it. And now you're trying to play with this object, which is product of semi-infinite matrices, and you find that it has some rather interesting properties. Namely, it turned out that even though it's rather complicated matrix, you could always apply similarity transformation to simplify it. And indeed, what we found that there exists similarity transformation, which basically brings it to block diagonal form. And at the end of the day, once you have this representation, you could always rewrite the square root of determinant of this matrix as being determinant of some integral operator, which is defined by this block here, K minus. And just to show you how this operator looks like, I just take arbitrary test function, acting on this integral operator test function, give me some integral back with some kernel, this K integral kernel, and some function chi. So function chi is the one which carries dependence on all variables in our problem. So it carries dependence on the coupling constant, into kinematical variables y and xi, which are related to cross ratios. And the K, most remarkably, is a very special function. This is a function which goes under the name of the integrable Bessel kernel. And this integrable Bessel kernel is known to be synonymous with integrability because it appeared in various problems like distribution of eigenvalues and random matrix models, Cardar-Parisi-Jeanc equations, and more recently so-called BS equations in context unequal force theory. So we're on the right track. This K function is a very special one. And now the question is, how could you compute? So now you have a representation for the octagon as determinant infinite dimensional operator. And it's not clear whether you gain something, right? Because you replace one animal by another animal, which is as horrible as the previous one. And at that moment that strong Szego limit theorem appears. So let me explain you what this theorem tells you about. So this theorem tells you about asymptotic behavior of determinant of special class of matrices whose entries basically have a form A, J minus K. So these are called templates matrices. And then Szego was the first who asked the question about the asymptotic behavior of determinant of such matrices. So take these matrices with indices I and J running from 1 to n. And the question appears, how does this determinant scales with the size of the matrix? So he realizes that if you take the size to infinity, it has exponential form, with the exponent being leading term linear and n, and then there is whole series. And now if you're thinking about this formula, you compare with formula we have seen before, like this one. You immediately conclude there is something goes on, right? So another way, if you replace here n by square root of lambda, you will see that this formula looks remarkably similar to what you would get from AdS CFT in classical limit. So, and you will see in a second, this is not accidental, there is something to this. But let me explain you ingredients of this formula. So once again, you have here a formula with n being large parameters, the expansion goes on powers 1 of n, the leading term a naught, b tilde, etc. They define as follows. First of all, you identify these entries, so these entries of these template matrices, as being Fourier component of some function defined in the circle. So you take some smooth function in the circle, you expand it over the plane waves, the corresponding coefficient and k are those which go into entries of this matrix. And now if you're looking for the leading term a tilde naught, it becomes related to the leading Fourier coefficient, not as a function a, by log of the function a. So this was so-called first Szego theorem, which has been formulated more than a century ago. So then the second term, which is b tilde, is defined by the sum, which involves higher mode components of the log a function, k minus k, and there is k in front. And then this formula was obtained almost 40 years ago, 40 years after the first one. So it took 40 years for Szego to formulate the second theorem. And then it was later realized by Fisher and Hartwig that actually if you look for the sum, it may happen that this sum is diverges. And it diverges, for example, when the function a vanishes and for certain values of theta, let's say theta 0 with some index beta. And then in this case, this b naught becomes divergent. And what it does you have appearance of the log n term with a1 tilde being related to beta square. So this beta has a meaning of like topological invariant. It's given by the exponent of the how fast function vanishes at a certain point. So why these formulas, why the theorem is useful? Actually, it has been realized by Ansager himself a long time ago. So what Ansager did, as you obviously know, that two-dimensional Ising model is a solvable model. So Ansager came up with an expression for spontaneous magnetization, which is correlation function of two spins separated by n lengths on the lattice. And then at some moment through the calculation, he was able to rewrite this correlation function as determinant of template matrix. And he struggled quite some time to compute it on asymptotic behavior. Finally, he managed. And actually, the way how this second Szego theorem was formulated, at some moment somebody has shown to Szego Ansager paper, and Szego realized that actually the paper of Ansager, even though it was completely incomprehensible, it was about correction to the first Szego theorem, and this is how he came up with second Szego theorem. And Ansager later admitted it was the rare example when the mathematicians did it first and physicists followed. Anyway, so this Szego theorem is quite remarkable because it tells you asymptotic behavior of certain determinant, and as I already mentioned, it seems to have direct relation to AdS CFT. And indeed, to see that, let's do one step more further, and then let's consider a very special case when this template matrix, which I defined before, actually deviates from identity by some small amount with 1 over n in some function k. And I put some g as arbitrary parameter inside the argument. Then the reason for such parameterization, because for n to infinity, this becomes well-defined object and it becomes integral operator. So this integral operator k now is defined as a operator acting on the interval from 0 to 2g, where g is parameter sitting here. And this kernel, you could play with different forms of matrix k to get what you want to get. And one of the choices gives you this. So one of the choices is known as the name of truncated Bessel operator, which is defined as some integral to Bessel function, some function chi, which could be arbitrary. And once again, this strong Szego theorem tells you asymptotic behavior of this Fredholm determinant in the limit when G goes to infinity. And here it is. So once again, you have something which is very similar to AdS CFT semi-classical limit, with G being coupling constant, with A naught and B very explicit formula. So now the question is what this has to do with what I described before. And as I already mentioned, here you have a formula which involves determinant of the K with some Bessel functions. It's not surprising that the same determinant turned out to be related to this determinant. This is what I wrote here. So you could show some one-line calculation that actually is exactly the same determinant which mathematicians introduced a long time ago, exactly the one which we're interested in, and this coefficient A naught and B is exactly those which will appear in semi-classical expansion of the octagon strong coupling. And the question is, what about this correction 1 over G? So in principle, you like to get symmetrical expansion 1 over G, and this Szego theorem doesn't tell you about 1 over G, but there is another method. And this method was developed by IPHT, etc. in the application of correlation function. It goes under the name of differential equation. I'm afraid I'm already running out of time, so let me be very brief on this. So the idea is that what these people notice is that if you introduce some logarithmic derivative of the Fredholm determinant with respect to coupling constant, this logarithmic derivative satisfies a number of remarkable equations. Basically, you could formulate using this definition of the Fredholm determinant, you could define exact equations, and this is the equation which I mentioned at the beginning of my talk. This is the exact equation with respect to all variables, y and psi kinematical variable G coupling constant, and they involve some auxiliary function Q, which itself satisfies differential equations. So this becomes some coupled system of integral differential equations with variables y and psi and G sitting in the same function chi. So now the question is, if you want to find the octagon, you have to solve the differential equation as a function of u, plug it into these equations, and then try to find u explicitly. And this is in principle a very complicated problem. In total, there is two limits in which this problem could be solved exactly. And one of the limits exactly the one which I described at the beginning of my talk, namely this light-like limit when you put operator in the vertices of a null rectangle. So which corresponds to the y into infinity psi fixed. So in total, this limit you could solve this equation analytically. And the result looks as follows. So I already told you at the beginning of my talk that you're expecting correlation function being exponentially small with the link term being y squared times function of the coupling constant, and here it is. So this function of the coupling constant could be found in this limit analytically. It's just this, log cosh. Moreover, we're able to also compute subleading term, this function c, and also given by rather nice representation. And now, okay, obviously it satisfies all conditions, agrees with the coupling expansion. And now something interesting happens. So now once you have this expression like this, so it's a clear formula function coupling constant. Let's now go to the strong coupling limit. But it's not conventional strong coupling limit because first we put y to infinity and then g to infinity. And so we will find that this function has very nice form, leading term g, constant term, but there is no 1 over g corrections. By some reason which you don't quite understand, this series in 1 over g truncates. There's something which we haven't seen so far in AdS CFT. So it looks like something goes on, and it's ultimately related to this unconventional strong coupling limit. Then you go to the conventional strong coupling limit, namely you fixed kinematical invariance and you put g to infinity, so you change order of limits. And then in this case, you do expect semi-classical expansion to appear, and it's there. And as I already explained you, the first three terms come from this strong Szego theorem. So we know A naught, A1, and B from the theorem, but A2 and 3, etc., we don't know. But if you go through this system of integral differential equations, you could get them. And at the beginning, there was a question, do we expect some functions appear at strong coupling? And I told you there will be one function which will appear at strong coupling. Here is the function. So this function I with subscript n is the one which defines strong coupling corrections to any order 1 over g. And this given by this integral representation with psi and y, once again, kinematical invariance. So the leading term A naught coincides with what has been known before. Term A1, I told you, it has some topological meaning. It's 1. And all other terms could be computed explicitly. So at this point, we know expansion of octagon strong coupling, and you ask the question, what are the properties of this expansion? How does it compare with the correlation function? And what we do, we did some experiment. So by experiment, I mean the following. You choose some particular kinematical points. So for example, you fixed value of kinematical invariance xi and y. And then you try to compute your correlation function using two different representations. The first representation, it was this Fredholm determinant or determinant of semi-infinite matrix. So you cut matrix to some reasonable big size, and you compute this determinant numerically. And secondly, you compare the result with the strong coupling expansion. So you use my previous representation, so this representation here, you replace kinematical invariance by their values, you get some numbers, and here it becomes the series expansion, a strong coupling. So leading term, log term, and series 1 over g. At this moment, also something interesting happened. If you look for the series, first of all, you will notice that sufficient high number of loops in 1 over g. Coefficients start to blow up. And indeed, you could show that they blow up factorially. So you're dealing with asymptotic series. But since the signs are alternating, the series is Borel summable. What does it mean? It means that even though series formally is divergent, asymptotic series, you could always improve it. You could play different tricks to improve it and to get out of the series a function which approximates your result with arbitrary accuracy, which allows us to compute this log of the octagon using this representation for relatively modest values of the coupling constant. And here what happens. So on this plot, I'm showing two different curves. So one curve, dashed line, it corresponds to strong coupling expansion. So on the vertical axis, I put log of the octagon over g. So the linear behavior is linear in g. Therefore, if you divide by g, it becomes a constant. Here's a constant. So if you start from the infinite coupling constant, it becomes this. And that small value of the coupling constant, I use perturbative expansion. So this solid line is V coupling expansion. And this solid line coming from strong coupling is the result of the resummation. And you see that the two curve describe whole range of the coupling constant, and somewhere around g equals 0.5, there is change of the Stoney behavior. But anyway, this curve, this picture to me is rather convincing to show that formulas are correct. So at this moment, we conclude that we have very good description of the octagon for both at weak and strong coupling, and hopefully there is a way how you could merge the two to get description for any value of the coupling constant. And finally, let me conclude. So let me summarize what I have shown you. So we started from the correlation function of 4 half-BPS operator, and then we consider a very special limit when these operators become infinitely heavier. And this limit, some interesting things happening. So namely, we found that using the integrability approach, that this correlation function satisfies exact system of the equations, which could be solved in two different limits, a null limit and a strong limit, thanks to this Szego theorem. But there's a lot of questions which are left over. First of all, one of the crucial steps in construction was simplification of Fredholm determinant. So we've seen that there is some simulated transformation which allows you to factorize, to simplify form of the infinite-dimensional matrices. We don't quite understand the reason for this, but it should tell you something about the structure of the theory. And second question is about strong coupling expansion. There's many different examples of when such expansion could be developed systematically. One of them, for example, Caspar anomalous dimension. And those examples, the series which you obtain at the end is not Borel summable. It has Borel singularities. In the case of correlation function, which we have here, we don't have Borel singularities, which means that somehow at the limit when this R-chat of the operator goes to infinity, you're killing all Borel singularities. Also, the reason kind of obscure, we don't quite understand. The next step that it was very important to go to the limit when all operators were infinitely heavy. And obviously, the next step would be just to look kind of perturbative expansion when you treat those operators heavy, but you're expanding correlation function inverse powers of their weight, and hopefully there should exist a way how you could include the description correlation function with light operators. Just to get things even more mysterious, so I have shown you that the light limit, there is 2 anomalous dimensions which we're able to compute exactly. And those anomalous dimensions when controlling light behavior 4-point correlation function. Recently, there was a paper by Bessel, Dixon, Portanazio, in which they asked slightly different questions. They looked for a completely different object, which was 6-point amplitude, and they looked for asymptotic behavior with amplitude in some degenerate kinematics. And by some reason, once again, we don't understand, they found this asymptotic behavior controlled exactly by the same anomalous dimension. So it seems that there is very intricate relation between 4-point correlation function in light limit and this 6-point amplitude in this degenerate kinematics. Also, we don't understand why. And last but not least, my description was entirely planar. So there's always a question, what happened about non-planar corrections? We do believe that integrability is there, but it will be very interesting to understand whether it's possible to generalize the whole construction to incorporate those non-planar corrections. And let me finally thank you for your attention, and sorry for taking too much time.
Well, thank you very much, Grisha, for a very nice talk. Let's all please unmute and thank Grisha. Any questions?
Sorry, somewhere in the middle of your talk, you presented these integral differential equations that your octagon obeyed. I missed where those equations came from. What was the physical source of those equations, please?
So you start. So you have this octagon. So octagon for the octagon you have this representation. So this representation. You start with this C formula. So this formula defines your calligraphic O uniquely.
Where did that formula come from, please?
This formula where it came from.
Yes.
Sorry. So you start from this formula. So this formula tells you it's come from this integrability business. You get a representation with determinant of some semi-infinite matrices. Okay?
So this is something we have to know.
You have to accept it because it comes out of the integrability construction.
Okay. Thank you. Thank you. Yes.
And if you wish, if you let me say one word. If you expand this guy in powers of this matrix, so if you wish this matrix C times K times lambda, it's describe your contribution of psi. So each psi give you matrix like that. So if expansion of determinant powers of this guy corresponds to the expansion of the sum of powers of, in terms of psi. But to get this formula to this representation, it took quite a lot of work of people inside the integrability community. It's not something which you could just get on the envelope.
Okay, sorry, one more perhaps related question. If you compute this 4-point function and you expand it in OP expansion, you should get in the middle the spectrum of all operators that can run when you bring two of them together.
Yes.
So somewhere in this formula, you should also see a formula for the spectrum of the theory, presumably for very long operators. Can we see that?
One question of caution. So in normal situation, let's take OP expansion. So once again, you collide two operators, you have operators which are changed. Now, at the moment you put two operators, two heavy operators, you're paying a price. Price is the following one, that you have huge degeneracy of the operator. Think like this. You have two operators, you collide them and you look for operators, exchange operator with certain quantum numbers, let's say twist, spin, whatever. Then if there were just operators of lowest weight, 2, then you just colliding two representation conformal group, you get something in the middle and there is no degeneracy. Another way, there will be only one operator in the OP propagating with given quantum numbers which are spin and leading twist. Now, if you have operators which huge scaling dimension, and you look for the operator with leading twist, you will have quite a number of operators with the same twist and with the same spin. Which means that if you were doing OP the way how you described, then at the end what you will be obtaining, you're obtaining OP data for not for single operator, by averaged over those huge degenerate operators.
Okay.
And
sorry, these operators are exactly degenerate or degenerate in the large K limit or something?
No, they degenerate. No. They degenerate to any ordered decoupling expansion independently on the value of K. If K is bigger than 2, as soon as K bigger than 2, you will have degeneracy of the operator. The number of operator will be degenerate. It will scale as the power of K. So if K goes to infinity, obviously the number of degenerate operator will be increasing. But the difference between, let's say, twist 2, so it's think like this. So you want to construct an equal for serial operator with given quantum numbers, like a twist and spin. Then for operator twist 2, there is only one operator. For operator twist 3, for given spin S, there's S plus 1 operator for twist 3. So all of them degenerate at any order decoupling. So if you increase now twist 4, etc., it will number of operators with the same quantum numbers will scale as S a spin in some power. See? So therefore, it doesn't matter for any values of K bigger than 2, you will be dealing with degeneracy. But k to infinity becomes, in that case, very special limit. The number of operators will become infinite.
So why don't coupling constant effects shift this degeneracy?
Because okay, things like this. So you have dilatation operator. So you have dilatation operator. You construct it. You have some basis of the operator, those degenerate operators. So you have some mixing metrics which you want to diagonalize.
Yes.
So then at zero value of the coupling constants, all those operators have scaling dimension, which is naive scaling dimension. Then each of them gets some anomalous dimension.
Yes.
The first question, why those anomalous dimensions are different? Why there is no degeneracy at the level of the anomalous dimension? The answer to this question is related to so-called non-crossing theorem, namely that if there were degeneracy, it would mean that, like in quantum mechanics, imagine you have some Hermitian matrix, and you know if there is no any particular degeneracy, if the matrix kind of sparse, then you know that eigenvalues will be different. There is no crossing of eigenvalues. There is no way how two eigenvalues of Hermitian matrices will degenerate for any value of the parameter.
Yes.
The same happens here. So if you start with mixing matrix, and you know those operators have a right to mix, in other words, there is no any quantum numbers which prohibit them to mix. They will mix. And the moment they will mix, the mixing matrix will be Hermitian matrix. The Hermitian matrix will have distinct spectrum of eigenvalues.
Yes. So,
which means that as soon as you turn on the coupling, anomalous dimension will become different, and this operator will get.
And what is controlling that splitting, please? What parameter controls that splitting?
Coupling constant. Coupling constant.
Lambda. So then when we're at lambda equals half, there's no degeneracy at all. So why can't we pull out? Why can't we pull out the anomalous dimensions rather than average anomalous dimensions?
No. Sorry. You're talking for lambda not small, finite number of lambda. Okay. Now, what you're saying is that okay. The thing which you have to verify. Okay, so if you're saying let's take lambda finite. For lambda finite, spectrum of the scaling dimension will be discrete.
Yes.
Now the question is, what's the size between let's say neighboring eigenvalues of the mixing matrix? Since you have number of operators infinite, if number of operators infinite, the spacing between operators, naively you should expect it should scale also like 1 or some k. Another way, if you go to the limit k to infinity, I'm not sure that you will still be dealing with a kind of discrete set of the operators. There will be.
I see. So what you'd be able to get out is some sort of density of operator. Density.
Exactly. As I was about to say, that in this limit k to infinity, the right quantity to look for, it's not any given level, but introduce density of the states, and then the OP will give you kind of average quantities of density of states.
Nice. Thank you.
More questions? So I have a tangential question. These types of 4-point functions, 4-point functions of BPS operator recently were studied from the Mellin space point of view also.
For finite k. For
finite k, yeah. Would that language help this discussion at all?
I would say that it will be great. Let's say you see that if you're thinking from a point of view Mellin space, so think about this relation. So if you knew Mellin space representation of the gamma, then so we know that this octagon or some kind of fundamental object, it's simpler than the correlation function itself. So my question would be writing Mellin representation for the square function, it will kind of obscure the property. Another way, if you knew Mellin representation of the gamma, with calligraphic gamma, it will go k to infinity. You should see at some moment that the Mellin space, it will be more natural to write this Mellin representation as convolution of two Mellin representation corresponding to octagon. On the other hand side, as you know, these lead integrals. So once again, at weak coupling, this octagon is the sum of the lead integrals. And lead integrals, they have very nice Mellin representation. They're very good. So therefore, one thing one might try to do is just start with Mellin representation at any given number of loops, and try to see whether you could go from a representation of correlation function of the ladder to a representation of the octagon. Because I'm pretty sure that octagon is much nicer than function itself. So if there is something happening at the level of representation, it will be a representation for octagon rather than for correlation function.
I see. Okay. Thank you.
But obviously this question has not been explored yet. So
More questions? If not, let's thank Grisha again for a very nice talk.
thank you very much for organizing my talk.
Thanks for the wonderful talk, Grisha.
Thank you.
Thank you very much. Thank you all. Be safe and stay healthy. Huh?
Yeah,
Really difficult time. Huh?
yeah.
Bye bye.
Bye bye.